My name is Mengqi. I'm an undergraduate student from Beijing University of Post and Telecommunications. And my topic here is about the cooperative deep reinforcement learning for traffic signal control. And here is the outline of what the problem is and what the challenge we are facing. And it's like, I'll just read it because I'll talk about it in details in the following slides. And the first one is increasing traffic pressure, and it's always need human correction for in some specific times or in some conjunctions, and different intersections work independently, like in modern approaches that the researchers are always focusing on a single intersection instead of treat the matter together. And the last one is that the traditional measurement doesn't help for individual rights. It's like that. It's our own feeling about if we are waiting for too long, or if the situation of the traffic is just okay. So the measurement, the average waiting time, is not suitable for our own rights. Yeah. And now let's talk about what we are facing and our solution in general. Yeah. The first one is that increasing travel demands. Yeah, people's living standards actually is increasing now, and lots of families own more than one private cars, which bring significant pressure to the road network. And this question is even more obvious in China, in Beijing. Yeah, and what matters is not only the prediction of flows and how many traffics will be generated for a specific intersection or in a certain region, but also the appropriate control to keep the traffic in order in normal situation. And what we are going to do is to alleviate the possible congestion when traffic demand goes high, and that is what we are going to do with the problem of traffic signal control. Next, I'm going to explain why we are using deep reinforcement learning technique for this problem. It's not of the question like I want to use deep reinforcement learning to solve some problem, so I choose a traffic problem. It's like this problem really needs the technique of deep reinforcement learning. Let's think about the situation I've just mentioned. If we want to take the road traffic into control, it will be nearly impossible to predict all the possible situations and program the traffic signals like what we are doing today. The traffic signals is act like one phase or several phases for different times of the day, for different weathers. If it's the advanced technique, it may consider the weather situations, like it's raining now or it's not. Yeah, but it will be much reasonable if we keep observing the road network and or several intersections and make decisions based on what we just observed. So if the situation of road network turns out to be better, it probably means that we are just doing something right. The action of our traffic signals is right for the current situation. And what I have just described is exactly what reinforcement learning does, especially the Q-learning. About the convolutional neural network, it is quite common to apply convolutional neural network in the dealing with road networks, since it's pictures, right? And the convolutional neural network is supposed to extract some deeper features or deeper relationship between the different points, different road segments, different intersections. So we are using the convolutional neural network here to extract some deeper features at the state inputs of the reinforcement learning model. Since reinforcement learning, here the Q-learning contains three parts in general: the state, the action, and the rewards. The Q-learning is I'll just explain in case that someone that doesn't know the reinforcement learning like Q-learning. Yeah, since it the reinforced learning is based on the observation of a certain environment or state, and it react to give some reaction, and what is observed, that is the environment, will give its feedback based on its the agent's action. So that's what reinforcement learning does. In our problem, although we are not dealing with road network in the real world, we are based on simulation of the networks, and I'd like to explain it a little bit, because I have been asked a lot of similar questions, like why we are not using the real data. This is because the government can't really take your advice and can't really let you to manage some public equipments. They need to know that your solution is effective and it will not do harm to the public, right? So in the early stage of our work, we have to apply them in the simulation networks. And that's why I'm not using the real data, since it needs an interaction between the environment and the program. And the next here is why traffic signals need to be cooperate. To illustrate the relationship among intersections, consider the following examples, as shown in the figure here. And when traffic flow at intersection A goes high, you can see it, I think. Intersection B and C may need to increase the duration of, let's just take the above as the north and the left as the west, Intersection B and C may need to increase the duration of west-east green light duration and the north-south green light duration. So respectively, so that there won't be future congestions at intersection B and C. Besides, since we are considering the problem of traffic signal control, which can be simplified to manage vehicles on the road intersection that are far away from each other, like what I have mentioned by Chair Zhengyu, and that out of some certain region, that some people or some flows may appear suddenly from a long distance. But in the traffic signal control problem, since we are considering the vehicles here, so if it's out of the certain region, we don't need to take it into consideration. This is because vehicles can move to distance intersections without passing through other intersections between them. It's a kind of increasing one by one. It's not going to be sudden changes. Here is why we are not using the existing techniques. The first one part is the traffic signal policy, what I mentioned at the slide 2, that most of them are using like one phase or several phase is programmed and cannot react to the what is happening right now. And the second problem, like the independent Q-learning, it has been proposed quite long ago, before the 2000. But it can solve the cooperative problem, but it cannot be used to a modern technique to speed up the computational time and to make it like run in parallel. And it's hard to deliver to other agents. Because I'd like to explain specifically here, since previous work about independent Q-learning is based on the idea of each agent will do their own work and at the same time. And for each of them, they will treat the others as part of the environment. So the problem is that for each agent, the state it is facing is changing, and the change is not made by itself. So, what I'm just mentioned that it can't apply to modern techniques. Let's take the experience replay, for example. And I think most of you who is kind of familiar with deep principal learning must be familiar with that. And in case you don't understand, and I'll mention it here. Since if we experiments replay here is that you state past experiments to a memory pool, and you just pick them randomly to avoid randomly from the pool for the when the future training to avoid some problem like that you are only focusing on the current problem, and you can't focusing on the whole network. And here, why the independent Q-learning can't be applied to the experiment pool, experiment replay, is because if we state the past experiments in a pool and take it out randomly, and for future training, the instability is going to increase. And among the random data that we are taking out at the previous step, it will not perform as the other deep learning models or other models. What you have just been taken out from the pool, there is no relationship between each other, and that's why we propose the cooperative deep reinforcement learning, and we are treating each agent is training independently, but each agent will also treat the other agents as part of the environment, and the other agents who is not training at the moment will following their previous strategy. That's the idea about the algorithm here, the cooperative deep reinforcement learning. And the next slide here is a comparison between if we use the cooperative deep reinforcement learning for the traffic signal control problem, or if we are just using the deep reinforcement learning for the traffic signal control problem. For the first one, is like I kind of take it from my paper. Yeah, it's like you can see that the line here. The line here is about our cooperative deep reinforcement learning. The result doesn't have too much difference, but it can convert faster than the deep reinforcement learning without cooperative in it, because since each agent is training and the other agent and the other agent, but the training agent's policy will be delivered to all of the other agents who is not training. And that is basically the reason. And the other one here is about is a measurement based on the acknowledgement that the overall cumulative delay. And it's based on our experiment, is the cooperative deep reinforcement learning will kind of significantly lower the overall cumulative delay, and it's better than the deep reinforcement learning, and more better than the only use Q-learning and the original policy based on the traffic signal control. Yeah. Here, and since I've just mentioned that we use the deep reinforcement learning, and the reinforcement learning is based on the state, action, and rewards. And here I'd like to talk about our state definition, because it's kind of different from the others, but it's a slightly difference. Here, the first picture, the first picture here, I'm not sure, okay, you can see the mouse, yeah. It's a vehicle's position. 0 means that there is no vehicle, and 1 is there is a vehicle, and the second one is the speed that is measured from 0 to 1. It is divided by the average speed, yeah. And the third one, sorry again. And the third one here is what is interesting, a little trick, and the traffic signal of the current intersection, of the other intersection, that is those who are not training at the moment. And traffic signal is actually happening at the intersection. But in the image-like matrix here, if we are represent it at the intersection, it will have some counter arguments with the vehicles passing through the roads. And if we use this way, that if the y here, y intersection is should be described as if it's green or it's red, and we will not describe it at the y intersection. We will, for example, this road segment, I'm not sure if you can see it or not. We will describe it whole as red. This way, we can not only describe the traffic signal lights, we can also describe like the road structure. Yeah, and the last one is the current intersection. It's for the learning that it's for the model that it can know which is my intersection, which is the others. And here in there's not too much slides left. Yeah, and here is the reward part. That's what I have mentioned. In our approach, we have taken the individual rights into consideration. Since our motivation here is that we are trying to help the people reducing their time consuming when they go to work, then come back to home and traveling, etc. Which means the effective of our solution is supposed to be counted as effective based on people's feedback. It's about trying to maximize each individual's own right. So on and so forth, we came up with the measurement that is the reward for the model inspired by the U.S. Bureau of Public Roads, BPR. That is BPR here. The function in transportation planning is kind of an exponential-like function. And to help understanding, that imagine you are blocked in an intersection and your way to work. You're probably not getting worried when you are just blocked for like 5 minutes, but when you are blocked for like 8 minutes, which is quite common in Beijing, you're a little bit nervous, but that's okay, right? But when it comes up to 10 minutes, let's say, I bet that you'll be really unhappy for the traffic situation here. And what I'm trying to say here is that relationship between the time that you have waiting and your own feeling is not a linear function. It's more like an exponential function, and it's just like the BPR function here. That if the traffic situation that will if there is more car on a road segment, the traffic pass situation will get really worse when it pass a certain benchmark. And that is also we are inspired by this BPR function, since that is if the waiting time is passed through a certain benchmark, every step of the time increment will cause a really big amount of unhappiness. Yeah, and the first equation here is a traditional approach, like the average delay. Most people use the average delay or like cumulative delay, this kind of thing. And the next slide here is a comparison between the different reward function, that is the average cumulative delay and our exponential-like function. Here, yeah, the figure 6 here. It's the figure 6. I'm so sorry. Yeah, the figure 6 here is let me see. Is the average. And this curve here is about the reducing of the average delay based on our CDRL model. It doesn't reduce quite a lot for average delay, quite a lot, but the results will not be bad. Worse than the DRL approach and our original approach based on the average delay. But actually the maximum delay, that is what we are really cared about. Which means that there won't be any driver, that any individuals that are waiting too long on the intersection. And so the maximum delay here is reducing significantly. And what the original approach does, like the cumulative delay, the maximum delay is quite large, and which means that some individuals must be harmed. Okay, here is the last slide. Yeah, it's the overview of our CDRL model to help you understand. This is what I have just extracted from the simulation of the network, the speed, the location, and the traffic lights, and it contains some road structure based on the traffic lights. Yeah, it's the input of our residual convolutional neural network, and here we are trying to reduce the choose the result that has the maximum possible reward, and to update our function. And I think that's all of my presentation here, and thank you for your listening. And this is my information here, and I'm looking for I'm applying for PhD now, and so if any of you is just looking for some students, please contact me. Yeah, thank you.